Moving forward, I guess through our RCP stages, Albert talked about offline simulation and the various design tuning that you do there, and moving that forward, generating your code and moving it onto real physical hardware. So what I'm going to start talking about is testing that code and trying to make it as robust as possible before you actually put it into the real power environment. So moving forward, one of the best techniques we've seen and we know of for this is using controller hardware in loop. This is where we're basically simulating our power stage in real time on hardware in the loop platforms. And the controller hardware is the just a standard off-the-shelf TI controller dev board, and the red interface board you see here is just a mapping of pins to that card. So using this, we'll basically be simulating the power stage, and you can see here in this example that I'll be running, I'll be plugging this code into a more complex microgrid with grid simulation, genset, a three-phase solar inverter, a battery controller, and a passive load. So in this example, we'll have one HIL 402 unit and a TI DSP development card, which we'll be using as our hardware. So moving forward, I'm going to give you guys a short demo in the Typhoon platform. Basically using this, you would move forward after your code generation and start testing your software algorithms to validate their functionality. And we're going to be doing this in the scenario of a microgrid. So this is the Typhoon HIL Control Center, which is basically the one spot that you should be going to for all of your testing. We developed all this in-house just to try to keep everything in one spot. So all the modeling is done in this software, the real-time control, and all the automated testing and the firmware management of the actual hardware unit. So jumping into the schematic editor, we can see the power stage for this example. And here we have a grid simulation, and we have some transmission lines to really give us that distributed energy simulation. We have some different faults, phase to phase, line to ground, and some more transmission lines. On this aspect, we have a simple genset model here. And this is all pulled in from our Typhoon library. There's an extensive list of different components here, which can be drag dropped and added as you see fit. So moving forward, we have a measurement block located in here, a solar inverter, passive load, and here we have the battery inverter. And you'll notice on this we actually have a little bit of signal processing functionality here. This just enables the user to go in and tune some things on the fly if needed, say if they don't have enough room on their hardware inputs and outputs and they wanted to simulate something also in the real-time environment. So this controller is actually modulated internally. You can see we take these measurements and then convert them into PQ or DQ and then modulate them into these gate drive signals. So moving into the real-time simulation, we can see here, as Albert showed earlier, the analog output mappings are defined here, and we have our source settings and contactors, PV, and we can go ahead and see on the scope, this is our grid voltage, this is our grid current, this is the current coming out of the simulated inverter controller, and this is the current coming out of the controller which is on the development board. So this would be the code generation. So moving over to this custom UI view, The only difference between the custom UI panel and the simulation control panel, they're both actually making the same API calls to this Typhoon software. So we basically have multiple avenues that you can go in and manipulate what's actually happening on your HIL unit. In this case, HIL 402. So using this SCADA-like view, it makes it a little bit easier to kind of see what exactly your system is doing. So right now we can see we have the PV monitor on, it's tracking. I can change some of these values and see things change. But if I go in and let's go ahead and move to the genset, you can kind of see the change in frequency here, and you can see the frequency correction happening. If I disable this load, you'll actually see that the PV is likely going to be unable to connect if I turn the load off. So you'll see on the scope that it's trying, but it's not quite getting there. So it has not connected, it's attempting, and you can see these frequency spikes. So if I go ahead and add this load, that should allow it to go ahead and connect. Great. So another functionality that is kind of built in here, which is pretty useful, is the ability to go in and do capture mode. So if we switch to capture, what we can do is actually took a previous capture, and I'll do another one here in a little bit. This is a capture of when the inverter was connecting. So here we can kind of see exactly what's going on, and we can add some cursors and do some measurements if we'd like. Another useful functionality is that you can go in and actually save this to a picture or a map file if you want to do some post-processing. So if we wanted to go ahead and do a force trigger, we can see our current data. Right now we're taking a 10-second sample. So this will take 10 seconds, and we'll see 10 seconds of data in full to view and manipulate as we want. But we can also go in and define a trigger. So we can take any signal that we'd like, digital or analog, and make this our trigger. So here you can see all this data that we've gone and collected.
What's the resolution on that, Ryan?
So right now, it's the model is running at 2 microseconds. So that's pretty much it. And then what basically defined, or it's defined on how much, what time base you set it as. So it's pretty much user defined. And you can change your samples and decimation appropriately. So for most cases, that's probably too many samples. So if we set it to 2 seconds, the data is a little bit more manageable here. Okay, so moving forward, what we can actually do is we encourage a lot of our customers to really test out the functionality of their controllers and make them as robust as possible. So one way you would do this is by introducing simple things like faults, so line to ground or line to line. So once this inverter goes ahead and connects, we can throw some faults in here. So let's throw a line to ground. You can see that it disconnected. It's okay. We can do phase to phase. And these are kind of simple fault capabilities that are built in, but we can also do some other things like some more complex macros. And what's actually happening behind these, I can go in here and show you guys some code. These are Python scripts. So on click, I will actually define these harmonics to be set. for all of these phases. And this is a little bit intimidating if you're not super familiar with Python, but we actually have a built-in code editor which really eases this pain and makes it very accessible for even not the greatest coders. So what you can do is actually go in and say, I want the grid simulation of this phase to be 220, 50 hertz, 0, and I can go ahead and add some harmonics. So it's very, we're still running in real time. I can define these harmonics, say OK, and I just click anywhere in the script and say insert. So this will add this other harmonic using those API commands I was talking about earlier. So regardless of the source, you can use these different commands to manipulate what your hardware-in-the-loop unit is actually doing and really provide some robust power. So for this code, let's go ahead and run those harmonics. And you can see I made some pretty heavy harmonics on that one. Let's set it back to nominal. We can also run things like a frequency sweep. I'll show you guys this code. So on click, I'll set the frequency, some step size, and I'm just running some for loops here to increase the frequency, leaving the phases untouched. And then generally as a final test, a good benchmark is a low voltage ride-through test. Specifically for grid-tied inverters, this is pretty important. So you can see I go in here and define some parameters, prepare the profile and set some scalings, and run a for loop to step these different phases through these low voltage ride-through tests. So I can go ahead and run these. You can see that the PV disconnected. And let's also run a frequency sweep once it gets back up. So you can see the frequencies are scaling here and our inverter disconnected. Okay. So now I've kind of put the grid in a unstable state at this point, so let's go ahead and make it back to nominal. I may actually have to reload to get this to work. There we go. Perfect. Okay. So generally, we encourage people to kind of develop these macros and test their generated code against these different test scripts that they write. And once you have these scripts written, it's all basic Python. So what you can then do is take these scripts and then start using them in an automated fashion. Using these other tools here with the script editor and test suite. So it allows you to interactively build these scripts to test your controller algorithms in real time, and which you can then use later in an automated fashion, which is probably one of my favorite features with the Control Center software. So moving forward, I'd say let's go ahead and move into some question and answer. And then we can call it a wraps for the day. Did anybody have any questions specifically on that demo?
Just looking at a comment, Ryan.
Sure.
So one of the things that it would be important here is with regards to the way this would all tie back together again, is you could use look at your response to these various faults inside of the real-time simulation. You could see if your inverter is acting the way your grid-tie inverter is acting the way you want it to, and if it isn't, you can actually bring those scenarios back to PSIM and work on fine-tuning your control algorithm inside of PSIM a little bit, regenerate the code again, flash back your DSP, and then try again quite quickly. So yeah, really, the key point here is to verify with all your testing with this hardware in loop in real time, and then make those adjustments and fixes or rerun those scenarios inside of the offline simulation, tune things up again, and then bring it back, generate more code, and bring it back to the hill simulation.
Yep. Yeah. The most, or I guess what we, the main point walking out of all of this is that before you move to your actual real hardware, the other steps of rapid control focused around the software are incredibly vital, just to make sure that your control algorithms are actually doing what you think they are, especially moving forward into microgrids where we have all these different components which don't necessarily know what other components are doing. So you have all these unknowns. So having a robust control algorithm really makes a difference.
Yeah, because in my simulation, I just had an inverter connected to the grid. I didn't have anything else. So I mean, the first step was to make sure that I was able to push energy to the grid.
Yep,
the next
yep.
step would be to start adding in, you know, doing fault testing, all that kind of stuff into my simulation to see what happens. But again, and importantly, making sure that we're going, when we actually go and connect, you know, a 500 volt solar panel that can do, you know, 12 kilowatts or whatever, we're not going to blow things up.
Always a good thing.